Okay, hey everybody, Dr. Urban, going with our second video in Chapter 7, which is Angular and Rotational Motion. In the first video, we remembered that when we have linear systems, which is what we've worked on so far, that we're moving in either the X or the Y, and we're going to need to get whatever unit we're given, maybe it's kilometers or miles or feet, we're going to be able to put that in meters. The rock slid 10 meters across the ice. That's the type of thing we're talking about. When we're in rotational or angular motion, things are going to be spinning. So maybe remind yourself there's some object that's going to be spinning. I want you to draw the little circle and do an arrow like this. Why do I want you to do this? Well, when we're in linear systems, you don't even need to do this because you're taught it so many times. We have learned that this direction, I'm going to use my red pen. This direction is the positive X direction, and I'm going to use blue for up and down. This direction, this way, is our positive X direction. Okay, we're taught that, so the positive X, positive Y, up is positive Y, down is negative Y. Well, when something's spinning, does it matter if it's spinning this way or if it's spinning that way? And this way and that way aren't technical terms. So what we do is we talk about rotation in terms of whether it's clockwise, so spinning like an analog clock, or it's spinning counterclockwise. So what I want you to do is from now on, at the top of every sheet you have for me, write C, C, W, and the positive. Counterclockwise is positive for rotation. So if this is the object we were talking about earlier, maybe it's object 1 here, and object 1 rotates this many radians to here, it has gone in the positive direction. That is a positive displacement. If we had, however, shown that object 1 rotated downward like this, that is clockwise, that is negative. So counterclockwise is positive. So ideally, you will write C, C, W, positive at the top of every assessment from now on to remind yourself that counterclockwise is positive. So moving on, we know that we're going to displace, but now we're not moving X or Y, we are rotating. And when we rotate, again, we traditionally think of rotating in units of degrees or how many times it goes around, like revolutions or laps. But we're going to need to convert that into radians, and this is your conversion factor. Well, what is the next thing we learned in linear motion? That we have something called velocity, and that is a change in displacement, whether X or Y, over time. So the velocity in the X direction is a displacement in the X direction over time. And since we're displacement over time, the unit would be meters per second. Okay, we have a similar type of thing in rotational motion, a parallel idea. How fast is it spinning? In the case of linear motion, this is the how fast. That's where we're talking about velocity. Again, we're here how fast, but we're going to be asking how fast is it spinning, or maybe rotating. And we don't use velocity because that's for linear motion. We are going to use what looks like sort of a scrolly lowercase w. It's actually lowercase omega. Okay, so lowercase omega, that is angular velocity. Okay, and if a velocity is a displacement over time, but angular velocity must be angular displacement, so it needs to be change in theta over time. How fast is it spinning, or how many radians per second? Okay, so therefore the unit must be radians that it's moving per second. Okay, what would I do next? Well, in linear motion, I have displacement, velocity. The next logical thing to talk about is acceleration. Acceleration is a change in velocity over change in time. So let's just stay in the X direction. We know that acceleration is in meter per second squared. Okay, and this is where we say, is it speeding up? Question mark, or is it slowing down? Question mark. So we must see, you've seen something spin and it spins faster and faster and faster and faster and faster, or perhaps you've seen something spin and it slows to a stop, like a top spinning. So there must be an angular acceleration. That is going to be the Greek letter alpha. Angular acceleration, acceleration is a change in velocity over time, but I have angular acceleration, so it's going to be a change in angular velocity over time. So it's going to be radians per second squared. Okay, now the really interesting thing as we move forward, let's zip forward, and this will be on the sheet provided to you. So we know we had some equations. I called this equation 0. It's just linearizing the velocity equation. So we would say that x final minus x initial, or change in displacement, equals velocity times time. That's just standard equation 0. I called this equation 1. Okay, equation 0. I called this equation 1. It's just breaking down acceleration and linearizing that. So it's delta v, change in velocity, or velocity final minus velocity initial, equals acceleration times time. You can find this on your equation sheet. Okay, and then what's equation 2? Okay, that's one of the other equations I gave you guys, and we had equation 3. So with equation 2, it is some kind of change in displacement. Oftentimes we're using this in the y direction, equals v initial y delta t plus 1/2 acceleration delta t squared. Okay, let's go ahead and write equation 3. That's v final squared equals v initial squared plus 2 acceleration delta x. So we've worked with these equations quite a bit. These are our kinematics. Okay, so then there must be rotational kinematics. So how would these look if we changed all of these equations over 0, 1, 2, and 3 in rotational motion? Okay, well, if equation 0 has to do with the velocity equation, let's bring that down here. So that is going to be a change in theta, or let's be even more specific, theta final minus theta initial equals velocity times time. Final displacement minus initial displacement equals velocity times time. These are in parallel. This entire thing is basically, or is the parallel idea, but for rotation. So it's the rotational equivalent of EQUIL, rotational equivalent of equation 0. Pretty much, okay. What was my equation 1? I need to use acceleration for that. Well, let's grab angular acceleration and let's see if we can make an equivalent for equation 1. So that is going to be, look, I'm changing velocity. I need angular velocity, so that's going to be delta omega, or final minus initial, equals angular acceleration times time. Let's review it. Linear systems, v final, sorry, there's a little, I wrote over that a couple times, v final minus v initial, omega final minus omega initial, equals acceleration, angular acceleration times time. Great. So this is basically the equivalent of equation 1. Let's keep going. Equation 2. Okay, I have a change in displacement. Change in displacement, that's going to be delta theta equals, I need a velocity, initial velocity times time, plus 1/2 acceleration. I'm in angular acceleration times time. So these are parallel ideas. So that's the equivalent of equation 2. And then the equivalent of equation 3 would be the same thing. So final velocity equals initial velocity. So omega final equals omega initial plus 2 times angular acceleration times some kind of displacement. That's going to be my equivalent of equation 3 for the rotational system. The last thing I need to do is, if I were a dot spinning, like I said here, I know that if this entire object, so I'm going to draw it a little bigger, It's making sure everything is fitting within the screen and I can finish this up. So if I have, you can pause there if you need to just go over this and fill in any information on the sheet I provided. But the last piece to go over is this. So here is our rotating disc, and it's rotating this way. So it is going counterclockwise and it is positive. So if it is rotating, and here's center of rotation, I have object A here and I have object B way out here. I know that if they rotate, let's try to show it rotating. B is going to rotate over to this place. So through this, on this arc length, so this theta. Well, A will be doing, and so this is the path that B takes. This is the arc length that B takes way out here, very long arc length. A goes the same angle, okay, the same theta, but it takes a shorter arc length. So you've actually probably experienced this. If you were on something like a merry-go-round, the closer you are to the center, you're still going through all the revolutions, but you don't feel like you're going as fast. Out here, this is where people are having the most fun. You seem like you're going really, really, really fast. So at any instant, I do have a linear velocity. I have a linear velocity, question mark. What is the linear velocity? So what is the velocity of B? What is the velocity of A? I'm going to go over that in the next video.